Hey, it's Mrs. Lethe, and we're going to continue Unit 5 with covalent bonding. Our first lesson, Lesson 6 on covalent bonding, is about energy and covalent bond formation. So the question is why do atoms want to bond? First, let's take a look at potential energy. Potential energy, when we're talking about bonding, is the energy that is available to form a bond or is able to react. Thus, atoms bond to achieve a complete octet, which is at their lowest potential energy. Lowest potential energy is chemical stability. When you think about that, what does it mean? When you're at your lowest potential energy, that means that there's very little energy that's available to bond or to react. So what's involved in a covalent bond? It's formed by the sharing of electrons that results in a molecule. A molecule is where we have two or more atoms that are covalently bonded, and it is the simplest unit of a covalent compound, unlike a formula unit, which is when you have thousands of positive and negative ions. A molecule is an individual separate entity of a covalent compound. Let's take a look at an animation of covalent bonding.
Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with one valence electron needs one additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still one short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay, so let's take a look at this potential energy diagram that we have here. Along the x-axis, you have the nuclear distance between two bonding atoms, and along the y-axis, you have the potential energy. Now, we're going to start here at this end of the potential energy diagram where we have individual atoms. Now these individual atoms, they're at zero potential energy because by themselves they're not interacting with one another, so they're not overlapping or sharing electrons. They just kind of exist. But as they're in constant motion, they move closer together. Then they start forming an attraction between the positive nucleus and the electron cloud. So you start having some overlapping taking place. And as you have that overlapping taking place, the electrons are starting to be shared. So now the potential energy is going to decrease. The closer they get to that complete octet, sharing those electrons, the lower that potential energy is going to get. So we're going to go down this hill. It's kind of like rolling a ball down a hill. But once you get down to the bottom of that hill, the ball doesn't stop. It goes up the other end. And so those atoms are going to pull closer and closer together, having a stronger and stronger attraction. But at some point, they get to the point where, okay, now they're too close, and those nuclei are going to repel, the electron clouds are going to repel, and so the potential energy is now way too high. And they're going to start pushing away from one another, repelling. And then they're going to go back up where they're too far apart. They're going to start attracting, and they're going to kind of go back and forth until the repulsion and attraction balances out, and though the complete octet has been achieved at the lowest potential energy. Once we reach that lowest potential energy and those electrons are going to be shared between the two atoms, that distance at the lowest potential energy is the bond length between the two atoms. Now, in covalent bond formation, here's what happens. If we take a look at the orbital notation for fluorine, we have two fluorine atoms that are going to form a bond. We see in the 2p sublevel that there's one electron that is unpaired. Okay, right here for this fluorine and right here for this fluorine. So what happens is their p sublevels, p orbitals, are going to overlap. And in that overlap, those electrons are going to be shared between those two atoms, completing the octet for each one of them. So here's what happens. You have a p orbital for one, you have a p orbital for the other. And what they're going to do, they're going to overlap, just like we have here. And that's what is forming the bond. Let's take a look at this in electron dot notation. We have our 7 valence electrons for one fluorine atom, 7 valence electrons for the other fluorine atom, and where those two lone electrons are, that p orbital will overlap, forming a complete octet. So those electrons are being shared between both of those fluorine atoms, completing an octet for one and also the other. Another way we can write this is by drawing a dash in between the two fluorine atoms, and that dash indicates a pair of shared electrons forming the covalent bond. So the number of covalent bonds in a single covalent bond involves the sharing of two electrons or one pair, and we can see that here between the two s orbitals of the hydrogen atoms. A double covalent bond involves the sharing of 4 electrons, so we can see the 4 electrons are two pair, and if we look at each one individually, okay, if we take a look at this carbon atom, has a complete octet. And if you do the same with the other one, you see that those 4 electrons shared between the two completes the octet for the other one. A triple bond is the sharing of 6 electrons or 3 pair of electrons. And that is the end of Unit 6. This is Mrs. Wheathy. So long for now.